But my basic goal is just to revolutionize our exploration of the solar system and the universe, so piece of cake. The problem is, space is big, and we are not exploring it at scale. You heard Caleb yesterday show the picture of almost 200 worlds in our solar system. Well, NASA has a New Frontiers program, which is a $1 billion mission, each one of them, and they've listed 6 top destinations out of the 200 worlds. And that's great, except that they're doing one every 5 years. So this is a 30-year generational program just to do the 6 top out of 200 worlds. And really in astrophysics also, the cost growth of the leading mission in each band of the spectrum is growing at about 10% per annum over the past 30 or 40 years, and culminating in $8 billion for the James Webb Space Telescope. And that's unsustainable in an economy growing at 2 or 3% a year, evidently. So we have to get the cost down, and that's where I came into this. So what I want to do is to enable an in-space economy in some way by harnessing capitalism as a tool to drive down costs, because that's really what it's good at. We need to cut mission costs initially at least by factors of 2 to 4, and that can then revolutionize the number of missions we get out in per decade, say. This is a reasonable number, and it may actually be happening. The reason it all works, of course, is that when you're trying to make a profit and stay in business, you really care about cost control, and that really isn't true of government programs. So, of course, everybody's seen SpaceX, and they've brought the cost of launch per kilogram to low Earth orbit down by factors of 3, soon to be probably a factor 5. There are people bringing the cost of satellites down, like OneWeb, who are going to mass produce these satellites, many per week. And so it's starting to happen, which is wonderful. And that is what makes space science, private space science, feasible, right? If you look at the size of 20th century astrophysics, astronomy-related foundation grants, they top out at around $100 million. That's the Yuri Milner level also. And the thing is, if we can make our missions cheaper, then we can get NASA-class missions for well under that cost. So a medium explorer in NASA terms costs about $250 million. If that goes to $60 million, suddenly we're in the right ballpark. They have a cheaper mission, too. The one shown, New Star, is wonderful. It's a small explorer, and it costs NASA $125 million, which would go to about $30 million. So now we're starting to get very interesting. And there are many fine ideas, probably 30 to 1 subscription to selection ratio for these explorer programs, every time they have an announcement. So a lot of great science is just thrown on the floor because of the cost. However, I'm an astronomer, and I'm pretty useless for most of these ways in which we can encourage industry in space. So for private space laboratories like this Bigelow Aerospace plan, this is a very realistic plan. In-space manufacturing, adventure travel, or even lunar mining, that's not something I can help with, because lunar mining is basically geology and I don't know about it. But the asteroids have the largest accessible resources in the solar system, and eventually that's what's going to drive the industry. And in fact, one single asteroid 200 kilometers in diameter contains the mass equivalent to all the mineable resources on Earth, and that means strip mining the entire land surface of the planet down to several kilometers. So it's an overestimate. It's actually even this small Lutetia, there probably has well over 10% of the Earth's resources in a single asteroid. So remarkably, when I started looking into this, very little is known about these asteroids. That we know they exist. There are 750,000 main belt asteroids catalogued, 15,000 near-Earth asteroids catalogued, growing at 2,000 a year. But very little is known about them. Even their orbits are pretty uncertain in many cases. So that means astronomers can turn out to be useful again, if they used to be back in the days of navigation and so on. So the problem with asteroids is not many of them are valuable. You've got to find the right ones. Not every mountain is a gold mine. So there's a few percent that we're really looking for. We want to throw away that grey, stony stuff and deal with the carbonaceous or metallic ones, depending on whether you're looking for water or precious metals, like platinum and palladium. So this is where we come in. My answer, let's prospect the resources of the asteroids using large telescopes on Earth, such as this Magellan 6.5 meter telescope in Chile that is partially run by the Smithsonian, also Carnegie. And 2, use professional astronomers. And you need professional astronomers because it's not easy to get these measurements. They can be done, but they need skill. So we're going to find our way. It's easy to, in fact, in principle, reject the 85% by looking at the color. Different rocks have different colors, and it turns out that the silicate rocks have a very clear absorption feature in the red end of their spectrum. So we can throw those out and just concentrate on the promising 15% of good ones for in situ prospecting. So we need to get out of a few, if it's only a few percent of good ones, we have to survey hundreds to get a good inventory of ore-bearing asteroids. So we can't afford to send spacecraft to all of them, but you can do it remotely. And we can do that with these big telescopes. I've studied this. You can cut the cost of prospecting the asteroids by a factor of 10 if you do your preliminary work on the ground. But it needs precision measurements, and this is where the professional astronomers come in. You have to know what you're doing to get accurate colors and accurate positions to at least the 1% level, probably better, to 10 milliarc seconds, which is a very tiny error on the sky, and we're developing means of doing that. I think I have a good approach now. It turns out because asteroids move, you have to get your signal to noise very quickly, otherwise they smear on the sky. If you want positions, you can't follow the asteroid because the stars smear, so you're stuck either way. So we need a 6-meter telescope. This one here will get these measurements in 1 or 2 minutes down to the faint magnitudes or faint objects that we're now finding. So that needs a new class of astronomer. Like geologists, most astronomers may end up working for resource extraction companies, and they'll be astronomical prospectors or applied astronomers. So. And this actually is going to remote sensing first. It turned out, it's pretty obvious I suppose, is how it works on the Earth. You fly over the zone and take photographs and things like that. You don't just go straight to start digging rocks. That would be a dumb way to proceed. So let's do it smartly for asteroid prospecting too. It turns out there's an opportunity. In a few years' time, the biggest Earth-based telescopes are going to be superseded by a new generation of much larger telescopes. This publicity still from the European Southern Observatories shows, in comparison with the pyramids at Giza, how big their big telescopes are. That's their biggest telescope now, an 8-meter. They have 4 of them. It's very good. It's a world-beating thing. But they're building this 39-meter telescope called the Extremely Large Telescope. The other one is just very large. And that will come online in the mid-20s, and as soon as it comes online, those smaller ones are obsolete. In fact, they'll look kind of quaint. There are 3 of these big telescopes being built. So these telescopes in the 6 to 10 meter range are going to have to find new reasons for being, and they'll need to sell time on them probably because the operating costs of these giant telescopes are going to suck up all the funds they have. So they will be looking for uses, and I think they should be repurposed to asteroid mining. So I'm impatient. I'm not going to wait till the mid-20s. You've got to refine your techniques. So let's begin. My plan is to use an instrument called PISCO, which I can explain to those interested afterwards, on the Magellan telescope. I can get, as a member of the Smithsonian, I can get 8 nights a year observing on this, no problem. We could possibly buy more, but that's something to investigate. And we can use this to get the signal to noise we need very quickly. That'll give us accurate orbits. It'll give us, and the colors will give us an idea of their composition, at least enough to reject those stony ones. It'll give us a rough size, because if we know the type of rock, we know how reflective it is, and that helps us work that out. And we can do this with only 8 nights a year. We can get 300 or so of these characterized each year, and that's actually doubling the current rate of characterization. The current rate is pathetic. It's 1/10 of the discovery rate or less. And I'm sure that as you start to accumulate large numbers of this, amounts of this data, it will also be directly useful for solar system science. So what I'm looking for, anybody want to jumpstart space mining, talk to me. And because our view, if we can do this, we will revolutionize our exploration of the universe. Just to put some numbers on, if we took a single telescope, 6.5 meter telescope, say, that would cost low tens of millions for several years, 5 years or so of work. The initial project for 5 years, just using a small fraction of the telescope, is much less. So let's talk. Thank you.
So, questions?
John.
Mark, how many suitable asteroids do you think you need to identify? And, you know, you're characterizing 300 per year, and you're probably, your yield of suitable asteroids for mining purposes is a few %.
Yes?
So, why is this not just a 3-year program? And then you have a dozen or so candidates that would represent a lot of resources, given the, how many asteroid mining companies are there now? Can we count them on one hand? And so, how long do you think you need to do this? And are the orbits, for example, very, very important?
Yes, so there's several factors.
Yeah.
One is you would like to have an inventory large enough that your launch time is not constrained heavily. And they have synodic periods. They come around again for their next apparition. Wonderful Harry Potter terminology they use in asteroids. The next apparition is several years, so 3, 5, 10 years even. So you need enough that when at any time you have one coming by. So you probably need dozens for that. You'd like to follow them for more than one apparition, because with the Gaia astrometric grid coming available, it's possible to measure very small motions and soon down to the microarc second, tens of hundreds of microarc seconds level. That may enable, I need to do the study, the measurement of their mass through the use of the Yarkovsky effect. So if you, which I won't bother to explain, it's too complicated. But it may mean, and knowing the mass is a huge advance, because although we may know the size of an asteroid and even what it's made of, they're usually got lots of, they're piles of rubble, most of them, and so there are big vacuums inside, and the density of the asteroids is far lower than that of the bulk material. And so you can't really just go from the size to the mass of mineable material. So it's very important to get follow-up observations on the longest time scale. Sydney. Oh, sorry.
Okay.
He's the boss.
Okay, I just wanted to, so thank you for your presentation, and I wanted to ask, you talked about, you briefly touched this, but you talked about how science industry can help commercial. How can commercial help advance, your research and the science industry? Is there low-cost instruments that they should be looking at putting on their commercial vehicles, or anything else?
Well, now that the launch cost problem is solved, which is wonderful, thank you. The next hurdle is the spacecraft cost, and I'm hoping that the communications constellations that are being talked about, like 600 satellites or OneWeb, will produce cheap satellites that are actually usable for large science instruments. And I'm trying to investigate that, and there isn't a lot of public information about them yet. But bringing down the spacecraft cost is the next big ticket item. And I'm sure that one of the great things about low mass to orbit is that you can throw mass at your design instead of eking out every kilogram or every 100 grams even, as I've seen happen in designing satellites. You just don't care. You've got plenty of space, you've got plenty of mass in, say, a Falcon 9, and that enables you to make cheaper spacecraft just like that, and probably enables you to make cheaper payloads, because it's only the optics and the sensors that have to be state-of-the-art like that. All the rest of those systems in the payload can also be made cheaper if you can throw mass at the problem.
So, have you been talking to mining companies, and if so, what's been their reaction?
Well, I've talked to the 2 asteroid mining companies, Planetary Resources and Deep Space Industries. And both of them are dominated by engineers who are very good at building small spacecraft and I'm sure they will succeed at building interplanetary CubeSat scale spacecraft for prospecting at the asteroid. But they were initially unbelieving of what I just told you, and one of the companies did eventually realize that this was a necessary precursor to their sending out satellites. The other still isn't interested.
I mean, actual mining companies.
Oh, big mining companies. I haven't heard of any big mining company who's interested yet. They apparently are very conservative. It's surprising, the initial exploration is not done by the big mining companies. They're called the majors, and they just rely on information coming from the miners. So they'll wake up and take interest once there is proven resources out there to mine. And then you get into the property issues we were beginning to talk about yesterday, because how can you stake a claim? If you normally you have to make your claim public and say, I found this value of ore at this location. And you can't, if you do that with asteroids, you're just giving it away to everybody. So that's an interesting situation.
The U.S. Geological Survey has a legal mandate, congressional mandate, to assess global mineral commodities. Have you ever talked to them about if they see themselves having a role in the future?
There was just like last week, there was a paper out from an astronomer, an asteroid astronomer, and the USGS trying to begin that process. And they just did a statistical look at the situation. So I'm now actually one of 2 professional astronomers in the world who takes asteroid mining seriously.
You have one.
What's his name? I'll remember in a minute. Sorry.
One and two.
This may be a tenuous link, it probably won't go anywhere, but your comment about approaching mining companies, Freeport-McMoran, Robert Day, who's the president of the Keck Foundation, is on the Freeport-McMoran board.
Okay.
I mean, it's
Let's talk.
conceivable at some point that might be.
I'll use any method.
But he's on the board of Freeport-McMoran.
Oh, wow.
I mean, say you got some portion of this funded by Keck.
Yeah.
That might be one idea. You know.
Great.
But you can't go to Keck with, say, I have an asteroid mining proposal. It's
No.
got to be.
Well, if I do it, right, there are 2 ways you could do this, right? I would do it as a member of the Smithsonian. It would be public information we'd be giving out, and it would do both solar system science, and it would enable space mining. You could also structure this as a commercial venture where you buy time on a telescope, or you buy the whole telescope, and over several years you accumulate intellectual property, which are the orbits and the compositions, and then you can sell it to asteroid prospecting companies. And I'm not doing that, but a group of friends of mine have started a company called Art and Engineering, and they hope to do that.
One thing that might fly with a policy like Keck is just packaging up the sensor part of it, where you're attempting to fish out 15% of useful mineable asteroids from the US.
Yes, that's an easy one.
Yeah, that's.
There was someone back there.
I'm just wondering, apart from the cost, what would be other constraints? Apart from the cost, what would be other constraints
On what? Do you mean on what I want to do, or on mining of asteroids?
What difficulty do you see doing this, except you need funding and time on the telescope? Is there any?
No, I think there's some detailed stuff I have to work out and do the studies for, like just how much better the orbits can be. We're doing simulations right now, but I don't think it's inherently very difficult. It's just seeing the application. It took me a long time to write this.
What's the most viable precious metal, like rare earth metals?
No, well, because of the cost of doing things in space, you have to find things that are worth a lot per kilogram, right? Moving things around the solar system is prohibitively expensive because of the rocket equation.
So right now, what is the most viable?
Right, there are 2, platinum and palladium. So most of the platinum on Earth is, point to it, there, 6,000 kilometers down. Right? All the iron in the platinum, these precious metals are rare because they dissolve in liquid iron and they sink to the core of the Earth. The remnant fragments in the crust are really a tiny fraction. Whereas in the asteroids, the same process happened, but then they got smashed to pieces, and so you're left with pure core broken up into iron asteroids. So you can find like a quarter of the iron meteorites are about 5 to 10 times richer than the richest mine on Earth. So that makes it promising. They're worth $50 million a ton in platinum and in palladium, both.
How do they compare with dissolved precious metals in seawater, which is considered a great potential resource?
I don't know exactly, but that's a very low concentration, so you have to go through vast amounts of it. So then it becomes an economics question of, is it cheaper to get it from space, or is it cheaper to get it from the ocean?
Because you're also then affecting the ocean and the life forms.
Yeah, there might be some serious issues there. Okay.
I have one last question. I started my life as an amateur astronomer. Is there any chance to crowdsource some of this work to amateurs, or it's crazy?
I would love to, and it used to be that amateurs provided very good information. I think we could do better than we're currently doing with the bright asteroids. I would love to gather not just what now gets reported to the Minor Planet Center are their reduced coordinates for the asteroids at various times. I would like to take the actual images, because now it's feasible to download them, because now you can retrospectively apply new positioning algorithms using the Gaia data, and you could improve orbits of existing objects, but we kind of lost that possibility. We could start now, we should start now. But most of the asteroids being found now are 20th or 21st magnitude, which is pretty darn faint, too faint for any amateur to really follow up, I think.
Even for very rich ones with freaking big telescope?
Well, maybe, but it's tough.
Okay, so it's not gonna work.
Yeah, I wish I could find a crowdsourcing idea.
Okay, hey, thank you very much. Fascinating.